All right, greetings everyone. Welcome to the second part of the video for section 1.1. Continuing on with our study of functions and looking at some more things related to them. All right, so before we jump into some new stuff about functions, I just want to review really quickly the ideas behind function notation. So we had this example we looked at where we saw that student name was a function of student ID number, and so we had the variable n to represent student name, I to represent student ID number, and then the variable f to represent the function. And here, since student ID number, or student name, excuse me, is a function of student ID number, we can write this as f of I. Remember, this is read f of I, not f times I, equals n. And again, in this setup, I is our input variable. Our input value, n is the output variable. Okay, so that's our function notation. So let's look at using this in an example. So we have two examples actually. So the first one up there says a function g, where given that g of holiday equals the month it's in. So in this function, the inputs are holidays and the outputs are the months that they're in. So because of that, they say g of Halloween is in October, or is October because Halloween's in October. G of Labor Day is September, since Labor Day is in September. And then they want us to find x if g of x equals November. So first of all, before we find the values for x, or the things that can be in there for x, let's identify inputs and outputs here, right? So in this case, the variable x, or whatever x stands for, those are the inputs. Okay, so those are the holidays, they go as the inputs, and then the outputs are the months. So November would be our output here. So we need to find the input, or inputs, that would give us November. And if we think about this, holidays that are in November is really what we're looking for here. Well, perhaps the first one that may come to your mind there is Thanksgiving. Okay, but are there others? Well, there's also in November is Veterans Day. Okay, so that could be a value for x. What else? I believe at the beginning of the month is Dia de los Muertos. Okay, there's also Indigenous Peoples Day and several others that I'm not thinking of right this moment. But hopefully what you see is that there are a lot of possibilities for what the value for x could be here. So many values of x could give us November as an output. Now, based on that, is this a one-to-one function? The answer would be no, right? Because in this case, we see that there are many inputs that give the same output. Now, it is still a function because each of those inputs only goes to a single output, right? Inputting Thanksgiving in this function will always give November as the output. Inputting Veterans Day will always give November as the output. The thing about this one is that there are multiple inputs to give us the same output. All right, next one says C of P gives the cost in dollars of grooming a poodle weighing P pounds. So it looks like in this function now, P is our input. Okay, and it looks like P stands for pounds. And they don't give us directly an output variable, but in this case, it looks like the value C, or the cost, that would be our output. And so we're asked to interpret what C of 20 equals 30 means. In other words, they want us to describe in words what C of 20 equals 30 means in the context of the problem. Well, again, we see that the 20 here is the input. and that's going to stand for pounds. The 30 here is the output, which seems like it's going to stand for money. So it looks like if we input 20 pounds, we get an output of $30, which, since this situation is in the context of grooming a poodle, it seems that what we're being told here is that the cost of grooming a poodle that weighs 20 pounds is $30. Okay, and I won't write that out. But you can either rewind this and get that again, and or look at the transcript. So it's the cost of grooming a 20-pound poodle is $30, which I've been told is vastly, that'd be super cheap. I should probably update this problem. Okay, so now we're going to start looking at different ways to represent functions, and we'll have three primary ones. So functions as tables, functions as graphs, and functions as formulas. Although there are other ways to represent functions. You saw me do it with pictures a few minutes ago, or in a previous video, not a few minutes ago. Okay, so here we have three tables, and what we're told to do is for each determine if it represents a function, and if it does, then to find h of 2, so what we get when we input 2 into the function, and then also solve h of x equals 4. So there, now they've told us what the output is, and we need to find the input. So let's first look at determining which of these are functions. And first of all, to understand what's going on with these tables, notice that we have a column here that says x, column here that says h of x. So this one on the left would be potential inputs. The one on the right would be potential outputs. Okay, and if we look at this first one, does this follow the rules of a function? Well, I see 2 going to 4, 4 going to 7, 6 going to 4 as well. But it looks like in each case, each input, each thing in the left-hand column there, goes to a single thing in the right-hand column, right? 2 always goes to 4. 4 always goes to 7. 6 also goes to 4. Remember, that's okay for 2 inputs to share the same output. It's just that one input cannot have 2 different outputs. So this one would be a function. Okay. Well, let's look at the next table, table number 2. So here we have when x is 2, h of x is 7. When x is 4, h of x is 5. And when x is 4, h of x is 4. Oh boy. So we see a problem here, right? We have 4 being mapped to 5 and also being mapped to 4. So this one here, because we see an input going to 2 different outputs, would not be a function. All right, and then for the third one, we see that 2 goes to 7, 4 goes to 5, 6 goes to 4. So each input is only going to a single output. So this would be a function. All right, so let's go back now to the 2 that are functions. So we're not using the one here in the middle. And let's do the other parts of the direction. So we're told to find h of 2. So here they've given us an input of 2, which means they want us to find the output, which in this case we see is, okay. Now for the second part, we have to solve h of x equals 4, and write that down here, which means we need to find the input that'll give us an output of 4. Now notice for this first question, or this first function, there are 2 different possibilities, right? X could be equal to 2, so h of 2 gives us a 4. But x could also be equal to 6. So that's why I put 2 comma 6, because both of those are possibilities for what x could be to give an output of 4. All right. Let's do a similar thing for the third one now. So we have h of 2. So looking at what, if we input 2, what do we get as an output? It looks like we get 7 here. And then also solving h of x equals 4. So we're looking for an input that'll give us an output of 4. And it looks like in this case, there's only one possibility. Right here, we only have x equals 6. So that would be our answer there. Okay. And that last part also helps to answer the final question here, which I know it's a little covered up. Let me try to highlight it. But which of those functions, if any of them, are one-to-one? Well, the first one, it looks like, is not one-to-one, right? Because we see that 2 is being mapped to 4, but so is 6. And that doesn't work if you're one-to-one. Each input has to go to a unique output. However, in this last function, in table 3, we see 2 goes to 7. 2 is the only thing that goes to 7. 4 goes to 5, and it's the only thing that does that. And 6 goes to 4. So it looks like this function is one-to-one because each input goes to a unique output, and or each output only has a single input that it's associated with. Okay. All right. Now the last thing for this video are looking at graphs as functions, or functions as graphs, I should say. So here we have 3 different graphs, and we're asked to figure out which ones are one define a function, and of the ones that are functions, which one is one-to-one. Now, first of all, I have to recall that the way these work is along our horizontal axes here. That's going to be where potential inputs would be, and then the vertical axis would be outputs. So for example, if this first one here was a function, I would identify inputs and outputs on the graph by looking at where it is along the horizontal axis and the vertical axis. So like this point I'm trying to highlight here, it looks like it's at -1, 2. So that would be an input of -1 given an output of 2. And recall that our conditions for something to be a function is that for each input there can only be a single output. So if we look at this first function, or first graph here, does that look like a function? And I think that it does, right? Because if we notice for any input, for any value we choose along the horizontal axis, like -1, 1, 2, 3, 0, there only seems to be a single output, right? From -1 we go up to this point. 0 looks like it has an output of 0. From 1 we go down to this point. At 2 we stay there. 3 we go up here somewhere. So that first one would be a function, again, because it looks like every input has a single output. So that one we can label as a function. Okay, what about the second graph? Well, again, if I look at any value along the horizontal axis, say like 1, we go up to here, 2, we go up to here, 3, we go up to here, -2 up to here, -5 up to here, -4 up to here, 4 up to here. So it looks like wherever we go, or any input value we choose along the horizontal axis, there's only a single output it goes to. So that one would also be a function. All right, the last one then, the circle. For this, if I look at an input value, like say 1 right here, well, I can go up to a value up here, or I can go to 1 down below. So it looks like for that input value, there are more than one output, right? More than one possible output. And we know that that's a no-no with a function, so this one here is not a function. Okay, so that one there is out. All right, so now that we've identified which ones are the functions and which one is not, let's now talk about one-to-one. So for this first one here, the first graph, going back to this here, could this represent a function? Well, for a function, recall that it means each input has to have a unique output, so no inputs can share outputs, which I think is a problem for this graph, right? Because notice, if I input -2 here, well, that would be at the point -2, 0, so we get an output of 0. However, here at the origin, we also get an input of 0 or we get an input of 0 given an output of 0, and similar for the point 2 right here. So this one would not be 1-to-1, right? Because we see that multiple inputs have the same output. However, for the middle one, we see that this is not the case, right? For any output we choose, there's only going to be a single input and only a single place where it intersects the or matches up with the graph. So this one would be 1-to-1, again, because each input has its own unique output. All right. And this leads us now to two different tests we can use to determine whether a graph represents a function or not. And I'm not going to write out the entire text of the tests here. You can look them up on in our textbook, but I will describe them. So the vertical line test, and what I will say about this, is used to determine function. Okay, so notice that for the first graph here, for example, anywhere I draw a vertical line, it's only going to intersect the graph in one point. And if we see that, then that means that this function or this graph passes the vertical line test, which means it does in fact represent a function. We can see a similar possibility for the second graph here. And we already know that's a function. But it doesn't work for the third one, right? Notice that I can draw multiple vertical lines that will intersect this graph in more than one place. So that's how we know that is not a function. And hopefully it makes sense why this test works, because we saw with the circle there that if we chose an input, we could go up and down and find two different outputs, right? But with the other two over here, we could not see that, right? If we chose 2 as a point here, we could only go up. We couldn't go down to get another output or go up further. Similarly here at 1, we can only go down to get a single output. So that's how that passes the vertical line test. All right, the horizontal line test then is used to determine if a function is 1-to-1. Okay, and basically the idea is similar to the vertical line test, is that if we can draw a horizontal line that intersects a graph in more than one place, then we know that is not a 1-to-1 function. So for example, for the first graph here, notice I can draw multiple horizontal lines there that intersect the graph at more than one place, and we already knew that one was not 1-to-1. But for the second graph, no matter where I draw a horizontal line, it will only impact this graph in a single location. Okay, so that one is 1-to-1 because it passes that horizontal line test. And similar to the vertical line test, hopefully the horizontal line test makes sense in that, if you choose an output on your vertical axis, if you can go both to the left and the right, or go left and further left and intersect the graph in more than one place, then that means there are multiple inputs that have that value as an output. Okay? All right, that's all for now. Thank you for watching.